Okay, so carrying on from that last talk, I'm most interested in the phosphate in the water there. And within this project, I'm trying to trace where the sources of this phosphate might be coming from. So as you just heard, various subcatchments of the Tor are failing for phosphate. So it might be worth just touching on what the forms of phosphorus are in the rivers. We tend to divide phosphorus into two forms initially, particularly insoluble. The border between the two being 0.45 micron. Anything larger than that we call a particle. Anything smaller than that we call soluble. And then we divide that again into organic. So organic forms, so you can have things like leaves, there'll be a large particle containing phosphorus, or soluble, such as organic acids like DNA. And then inorganic forms, so phosphorus associated with soil. Insoluble inorganic phosphorus would be the phosphate molecule itself, so which is the phosphorus associated with 4 oxygens. And it's this phosphate, which is what's monitored and we class as failing. The EA, when they sample, they look for phosphate and not the other forms. So as you just heard, really, these are the definitions of categorising the river, various catchments. The upper Tor, which I'm focusing on here, which is from Tor Bridge up to Tor Head, that's what we're currently sitting in as we speak. That's a type 2 river. Failing is classed as, I think, 40 micrograms per litre. Anything higher than that, I think, is deemed as failing. So again, going back to the EA data, this is Tor Bridge EA data. You've just seen in the previous talk, a slightly bigger graph this time. That's all the data from 1990 to present day. The red line at the bottom is that 40 limit I just showed you. And what you're looking at there is approximately 1 monthly sampling throughout each of those years. And the first thing you can see there is that there's an awful lot of peaks above that 40. And what's noticeable is these peaks all tend to occur in summer months, and the troughs tend to occur in winter months. And again, as you've just heard, that's been interpreted as a dilution effect with the low flows in the summer. What you're looking at is an increasing concentration, high flows in the winter, diluting the concentration. So in effect, the sources are remaining constant, the water is affecting the volume of water is affecting the concentration. But what we want to know really is what are the sources, and are the variable sources occurring at different times of the year? Are the same sources occurring at the peaks as the troughs? And that's where I'm trying to use some novel stable isotope tracing techniques. So now the science bit. What is an isotope? It's an atom of any given element that contains the same number of protons in its nucleus, but different numbers of neutrons. So on the left there is an example of the 3 isotopes of hydrogen. They all have 1 proton, but increasing numbers of neutrons. So tritium has 3 neutrons, deuterium 2 neutrons, deuterium has 1 neutron, and protium has no neutrons. Protium being the most abundant, making up over 99% of all the hydrogen globally. Deuterium much, much less, 0.02, and virtually no tritium at all. And the reason for that is tritium is radioactive and breaks down, whereas the other 2 isotopes are stable. They don't radioactively decay. So globally, they occur in the same ratio constantly. And the ratio, that's how we classify what the stable isotope signature of anything is. It's the ratio of the lighter isotope, the heavier isotope to the lighter isotope. Essentially, the only thing that makes them different is their mass. Deuterium is a bit heavier than protium. They have the same chemical reactivity, or at least sort of the same chemical reactivity. If they had the same chemical reactivity, everything would be made up of the same ratio of the 2 isotopes. There is a variation which occurs, which we call a kinetic fractionation, which is because of that extra neutron. In effect, that isotope is a bit heavier, a bit lumpier, and it takes a bit more energy to push it through any chemical reaction. So though it reacts along the same pathways as the lighter isotope, it reacts slower. So if you have a substrate that's being converted to a product, the substrate becomes progressively enriched in the heavier isotope as the lighter isotope is moved through the reaction quicker. And similarly, the product has more of the lighter isotope in as it's moving through the reaction quicker. So you end up with different ratios in the substrate and the product. And that's why different substances, different compounds have different isotope ratios, and why we might be able to use it as a way of tracing different phosphate sources. If our phosphate sources have different ratios, we might be able to see those ratios in the phosphate in the water. So, again, that sounds great, but we only have one stable isotope of phosphorus, so we can't have a ratio. But as you just saw, most P naturally occurs associated with oxygen, and in that inorganic form as phosphate, which has 4 oxygens. Fortunately, oxygen does have a couple of stable isotopes we can use. And the reason this works, in theory, is that the phosphorus-oxygen bond is resistant to breaking down in inorganic means at temperatures and pHs. So it's relatively stable in the water, actually. It's only when it's cycled through a biological enzyme-mediated reaction that we start altering that ratio. Some oxygen is lost and replaced with the oxygen from the water in which it's dissolved. So over time, phosphate in water gradually picks up the same ratio of oxygen as the water it's sitting in. So phosphate in water should, in theory, have the same, or certainly predictable, ratio judged based on the water value. Therefore, any deviation from that expected equilibrium could possibly reflect mixing of different isotopically distinct sources or alterations of that phosphate through biological processes. And that's why we might be able to use it as a tracer. As we just said, it's a relatively new technique. This is a graph summarising the 18O values for various sources globally in 2009. So that's all the information that was available in 2009 on what the ratio in different sources was. You can see there's not very much information. The wastewater treatment works down there. We have values ranging from about 8 to 20, whereas chemical fertilisers up here go from 15 to about 25. There's quite a spread, quite an overlap, and that might be a problem, because if we need distinct sources, if we end up with a mean value here and here, they're going to be quite close together. It's not necessarily a problem though when you go approach a catchment. You're only dealing with perhaps 1 or 2 sewage treatment works as opposed to 20. A few fertilisers within that catchment and a few animal waste. So as long as those sources are distinct, you can use it as a tracer. So within the partnership here, this is what we have been doing and are doing. We are sampling this upper Tor stretch from Tor Bridge at base flow, so we're trying to keep everything as comparable as possible. We don't want to sample in the summer during a storm and in the winter during a dry spell. We're trying to sample everything at non-storm flows, and looking at the phosphate concentration from the head down to Tor Bridge. We're also measuring that concentration at various tributaries entering the Tor at the point at which they enter, in most cases. So, as we just heard, so you're capturing everything that's going on above it. We're looking at the industrial effluents and the sewage treatment works that discharge into the Tor. And at various points along that, we're going to take some samples and look at the phosphate isotope oxygen ratio of the phosphate in the river water, in the tributaries feeding that, and of those discharges. We're going to try and characterise the discharges and the effluent, and also 5 other sources just within the catchment which may be contributing phosphate, so fertilisers, bed sediments, septic tanks, things like that. This is how we do it. We take our solid material up here and we extract the phosphate from it using an acid or water, and this whole process down here takes about 5 days. And what we're effectively doing is turning our soluble phosphate into a solid, pure compound, which we can then run on the mass spec. We turn it into a silver phosphate. And the whole process is designed really to remove organic matter and any other compounds which could contain oxygen and therefore confound our final value. With river waters, we flock out the phosphate. We add some magnesium chloride and sodium hydroxide. We form a brucite flock. It settles to the bottom and it picks up all the phosphate along with other things. So we concentrate all of our phosphate down here. We can throw away most of our water and then whack our flock through the same process. So some numbers. We haven't got many isotope numbers to show you at the moment. This is all largely concentration data from the last year. I have got a few isotope numbers to show you at the end. But back in March, we tried to sample quarterly to look at the different seasons, and again kept it all at low or base flow, however you want to define it. So up at Tor Marsh, you're looking at a relatively low value of 3, and that remains the same then at Digglepath. And the tributary we monitor in this upper region, Ford Brook there, again low, all fairly unexciting. We're exciting if you like clean water. That's the sewage treatment works just below Sticklepath. We sampled just above it, and the sewage treatment works at Sticklepath, which takes South Taunton and South Seal, had a value at the time of about 500 micrograms P. But fairly low flow. Again, without the rain, without the storm flow, the sewage treatment works is effectively just trickling out at a base flow level. Downstream at Tor Green, the next point you sampled below it, you're seeing a small increase. I guess that's unsurprising, really. And then at Newlands Bridge, just above North Taunton, not much change. And the tributaries feeding here, Wickington is fairly clean, Cocktree, a little increase, and the Bave, the stream there which flows out at the mill, is 36 micrograms P per litre. So these are, broadly speaking, higher than the river. Our main phosphate input there would appear to be the sewage treatment works. And you would suggest perhaps that these are leading to a small increase in the river, main river stem concentration. Below Newlands there, we've got the North Taunton sewage treatment works. When we sampled it then, we had a value of 4,000 micrograms P per litre. That is the delightful point we have to get to. And the cheese factory, which we also sampled, had a value of about 300 micrograms P per litre. So actually quite low. And you can see that the flow coming out of it, really, its contribution that would appear to be quite negligible, actually. Certainly when you compare it to the flow and the value of the sewage treatment works there. Rather unsurprisingly, the next sample point downstream, and we did take it a little way downstream, so we went round a meander, and I would say 500 metres around the corner, to give this every chance of mixing within the river channel. We see an increase of 33 micrograms P per litre, which then declines at Bondley, Torbridge, at 25 micrograms P per litre. And the tributaries all feeding that area are all lower in concentration than the river itself, so they would be leading to dilution, which is what we see. In June, so now we're moving on to one of the more summer months, and that previous graph we saw the concentrations tended to increase in the summer months. The upper part of the river, pretty much the same. The middle reach, now you're looking at Sticklepath sewage treatment works with a value of 6,000. And now you can see, now you can see an increase in the river directly below that. It's appearing to decline as we go down to Newlands, with water, broadly speaking, coming in at lower concentration, so it's diluting it. This stream here at the Bave, well, that's markedly high, really. It only has a small contribution in terms of flow, but it does flow off the Redlands. There's a strip of soil which comes through here, which is very distinctly different to the soil either side, which is sandy, red, very agriculturally intensively managed. Whether that has an effect on this stream, I don't know. The sewage treatment works now has 10,000 micrograms P per litre coming into it. And again, we're looking at an increase directly downstream of North Taunton. The river is now 400 micrograms P per litre. Interesting though, when you look at it, the concentration is increasing at Bondley and increasing again at Tor Bridge. We don't know why this is, why you would see an increase. When you look at the streams that are feeding the river, they are lower in concentration. We would perhaps expect to see, like with the previous sampling, a decrease in concentration downstream of here. The cheese factory, again, contributing, relatively speaking, quite a small amount. And the most recent sampling, we did this a couple of weeks ago. Upper part of the river, all nice and clean. The sewage treatment work at Sticklepath, still at 6,000. We're looking at an increase in the river, decreasing down to Newlands. Dilution, broadly speaking, from the streams feeding it, with the exception of the one. There's no discharge at the cheese factory when we're sampling it here at this point, so it's contributing nothing. 10,000 at the sewage treatment works. Now you're looking at, in the river at North Taunton, 1,500 micrograms P per litre, which is increasing quite dramatically at Bondley and Tor Bridge. We would expect it to be decreasing. Look at the rivers feeding it. They're all lower in concentration. What's happening here, we don't know. But it would seem to be, given the cheese factory is not contributing and the sewage treatment works would appear to be increasing it, there's some form of, either there's some dramatically large sources feeding the river which we aren't monitoring, or there's some form of phosphorus being released into the inorganic form as we go downstream. But that is definitely an area we want to look at further. I said I didn't really have many isotope numbers. This is it. The red stars are our numbers. This is the graph I showed you previously with the source values you just saw. We've done some fertilisers within this catchment. These are all collected from 5 farms. You're looking at numbers broadly comparable with those already reported. A bit of a wider spread perhaps, which doesn't help us with our distinct source tracer approach. The two sewage treatment works done in June, they're down here. They're again broadly in line with what's seen, a bit tighter together. Hopefully I'll have a few more numbers for these over the next few months, and we'll be able to see if they're contributing a nice tight signal. I'm also going to be doing some bed sediment in the next couple of weeks, hopefully some septic tanks, I say hopefully, inverted commas. I hope that's a brief overview and you've understood most of that. I put this at the end without realising that we weren't doing questions until the end.